time in geometry, do you remember the term induction? Like I said, compare inductive versus deductive. What is inductive? Or what would you see as the inductive thing? Or inductive reasoning? Anybody remember that? Okay. When you look at it, inductive reasoning is you look at a series of events and say, what is the pattern? What rule could I write from it? Or what theory could I come up with it? The problem with inductive reasoning is that it was not always true. For example, you could, example they often give in geometry book for inductive reasoning is, your neighbor, every Saturday, they ask you to let the dog out while they are on a trip. So what would your inductive reasoning be? Like if they do that for 5 Saturdays in a row, what would you reason? But about the 6th one. Would it make sense that you say, oh, your neighbor's probably going to ask me again, the next one? Now, is that necessarily true? No. But it fits the pattern. Here were deductive reasoning. Deductive was when you looked at a step-by-step method and saying, how do I get from point A to point B? And it's always true. You had a set of rules. You use, as long as you're using those rules correctly, you always get the same answer. When you add the 2 plus 3, assuming you're doing it correctly, every time you do 2 plus 3, you're going to get 5. Deductive reasoning, you're adding a series of steps, though, often. Like you do a proof, why is this, or why are these two triangles congruent? Like SSS, SAS, ASA. That sound familiar? Okay. Now, we're going to look at mathematical induction. It is a proof method that we're trying to prove something is true for all positive integers. Now, it does have a very specific strategy or very, very specific method that we do. So when you're doing this, the steps, the first thing you do all the time, so every time you're doing the inductive proof, you look at case 1 or n equals 1 case. And you show that this first case is true for whatever we're trying to prove. The first thing I'm going to write down the steps, and then we're going to look at a couple of these. So we're always trying to get the first thing is show that the first case is true. Second step. This is going to be the one that gets strange to you. We're going to assume that, so we're looking at what we're trying to prove, and we're going to assume that it is true. And we put for case K. Third step. Show that if K is true, then K plus 1 must be true as well. And this is the part where you start touching your mathematical thinking. Now, when you look at mathematical induction, the way you can think about it is, first step, show that you can step onto the first step of a ladder. So, if you think about it as a ladder, the n equals 1 case is just showing that you can step on the first step. The next thing you're trying to do is show that if you are on the ladder, you can go to the next step. So if I'm here already, I don't know what's below me, I don't know what's above me, but if I'm here, I'm proving that I can get from here to here without any worry about what's around me. So do you follow that general idea? Okay. And that's where we're going to run into our challenge, is showing if one case is true, then the next case must also be true. Now, why does this prove something? Well, we've already showed the first case being true. Therefore, if we know the first case is true, and if one case is true, the next must be true, then the second case must be true, right? Which means the third case, the fourth case, fifth case, all the way as far as we go, must be true. So if we can get onto the ladder, we can go as high as we want. That's what we're trying to show. Now, the steps to this. So let's look at one of these. So our goal is to prove, I'm going to go to another page, prove, and this is page 30 and 31, you'll probably need to use both pages. Can you look at several of these? So our goal is to prove 2 plus 4 plus 6 plus 8 plus all the way up to 2n is equal to n squared plus n. Now we can test a few cases if we wanted. So if I wanted, I could test 3. If I plug in 3, so if n is 3 here, 2 times 3 is 6. I'm doing 2 plus 4 plus 6. What do I get? 12. If I plug it in over here, 3 squared plus 3 is 12. I could plug in 5 and so on, but that shows it works for a few cases. But we want to show that it works for every case, no matter where we're at. So the first step, we need to show case 1. So case n equals 1. So on the left we say 2. Over here I'm going to plug in 1. 1 squared plus 1. What's 1 squared plus 1 equal to? 2. Therefore I get 2 equals 2. So is it true for the first case? Yes. So when you're writing these proofs, you would first need to show that the case n equals 1 is true. So then I say, first case is true as both parts are equal. Okay? So now I've done the first step, which says the case n equals 1. The next thing we're going to do is what? Okay, what does it say in the steps we just wrote down? Okay, so we're going to assume that it's true for the case. So we're going to write down here, and you do need to make sure write what your assumption is. Assume 2 plus 4 plus 6 plus all the way up to 2k equals k squared plus k. Okay, after we do the assumption, what's the next step? Yeah, so I like to label this as case k plus 1. So my goal is to show that if I have k plus 1, if I plug in k plus 1 into this problem, I get the same answer on both sides. So this is my goal. My goal is to show 2 plus 4 plus 6 plus 2k. What's the next case after 2k? Yeah, 2 times k plus 1. So it's saying if I had the fifth case, then the next one would be 5 plus 1, or sixth case. My goal is to show that this equals, what should this equal? Okay, what am I plugging in now? K plus 1, so what do I need to plug in over here? Yeah, k plus 1, so I'd have k plus 1 squared plus k plus 1. Because if I can show that this statement is true, then I've proven it. Because I've shown that if I can get on the first step, I can show that if this is true, then the next step must also be true. So, to do this, now, here's a hint. When you're doing it, you're always going to use your assumption. If you didn't use your assumption while you're doing this, then you did something wrong and you didn't get the answer you need. So I'm going to first use my assumption. Using assumption, the left part of this equation equals k squared plus k plus 2k plus 1. So, remember, my assumption was that this was true, right? This is my assumption. So, when you look at this problem right here, this part in yellow is the same as what I have up here on the left. So I can take this part right here and replace it with what it's equal. So I'm going to take this part right here, replace it with what it equals. So what does that part equal? K squared plus k. So that's where I get this k squared plus k from. And then we have this 2 part, the 2 times k plus 1. Everybody see that? That's probably the trickiest step, is getting from one part to the next. Anybody lost how we got this statement? The next thing we're going to do is we want to simplify this. What is this going to simplify to? So I'm going to distribute this. I'm going to get 2k and 2, so k squared plus 3k plus 2. Okay. Now we've got to operate on the other side. So usually I like to do this in 2 parts. I like to work on the left, simplify it as much as I can, then work on the right and simplify that. So this part, what's it going to simplify to? So k plus 1 squared is and I've got that k plus 1. Simplify this. K squared plus 3k plus 2. Are these the same? Okay? So I need to make, so once I've got these two, we can say both left and right are equal. This means that the assumption is true by mathematical induction. So whenever you finish this, we've got several steps. First, you've got to prove the first case. Second, assume what you're trying to prove is true, and show that if it is true, then the next case must also be true, the case after it. So when you're doing this, you will have quite a few words. This is a paragraph question. On the left, right here. Okay. So basically, what I'm saying is I'm using this assumption. My assumption is if I have 2 plus 4 plus 6 plus whatever all the way up to 2k is equal to that. So I'm not using this part. Think about it. There's a big division here. Let's go. Right. So I am not using the stuff on the right at all. I'm just looking at just this part. So if I'm thinking about this as an expression, not as an equation, how can I simplify it? Well, this part right here, because of my assumption right here, I can use it. So using my assumption, I can change this into what it equals. So I can use the left and right up here, but I can't use it over on this side. So it's basically like here are two separate parts. You follow that? Okay. Now, a lot of your proofs, a lot of these ones are going to be fairly simple. This is a rather straightforward one. You look at simplifying things, you adjust, move things around, do a little bit of mathematical focus, and you've got your answer. But you can also do some more advanced things with mathematical induction. So, prove n is less than 2 to the n for all positive n. Now we can choose several numbers and test them. 5, plug in 5, is 5 less than 32? Yes. Plug in 10, is 10 less than 1024? Yeah. But we want to prove it for all numbers, or for all positive integers. So this one is a bit more complicated than the last one. But you start with the same way. What's the first thing? Case 1. So case n equals 1. 1 is less than 2 to the 1. 1 is less than 2. Is this true? Okay? So I'm going to say because this is true, case n equals 1 is correct. What's the next thing you try to do? Or next thing you do?
Make an assumption.
Okay, assume. So I'm going to assume k is less than 2 to the k. Or I'm going to do k greater than 0. Yeah?
Is there a reason that you're using k instead of n?
Okay? Because n is in the problem, k is a variable that does not have anything to do, or is not directly linked to the proof. So I'm trying to prove it for n, so I'm working with k to show that in general it works. So k, in this case, because n is specifically what we're trying to prove, k is more general. It's like when you're saying 5 versus c, c is more general than 5. It's sort of strange, but it's a standard thing to do. Okay, and what's the next thing we're doing? Okay, prove the k plus 1 case. So I'm going to write down our goal. So our goal, because very often you don't necessarily have to write down what your goal is, but it's very helpful often so you can see where we're trying to get to, or what we're trying to do. Our goal is to show that k plus 1 is less than 2 raised to the k plus 1. Everybody see that? Okay. So next, very often I'm going to start by using my assumption. I'm going to say, using assumption, 2k is less than 2 times 2 to the k. What did I do to my assumption here? So what's the difference from here to here? Okay, multiply by 2. Is that a valid mathematical operation for inequality? Yes. The multiplicative property of inequality, or if you're remembering that. Now, how can this side on the right be simplified? What? 2 to the 2k? 2k is less than, no, because it's 2k, 2 to the 1 times 2 to the k. What can you do if you have the same base? what do you do to the exponent? Yeah, so for example, we had x to the third times x to the fifth. This is x to the eighth by 3 plus 5. Yeah.
So you multiply ignoring that, you would get 2k plus 1.
Yes. That was my goal, is so I can get that. So on this side, I'm going to have 2 raised to the k plus 1. So I've got this, right? Now I need to show that this part, how this part is connected to this part. And this is where it gets a bit trickier for this type of problem. First, notice we say k equals 1. We actually could go with k equals k is greater than 1. Might even be make better because we had our case 1. So I'm going to change that. Since we are starting at 1. And we're actually going to work with this part. K is greater than 1. This implies that k minus 1 is greater than 0. Alright, by that? This implies that 2k minus 1 is greater than 0. You see where that came from? Or do you see why it's true? What's 2k minus k? It's k, and so we get back to this. Well, if I know k is greater than 1, if I subtract 1 from both sides, I mean, k minus 1 greater than 0? If I subtract 1, well, not if, well, we're saying for all positive k. You know, when we look back at the beginning, for all positive k, so it should have said k greater than 1. Okay? Do you see where how this part is the same as that one? Now, this implies that 2k minus k plus 1 is greater than 0. So right here, I factored out negative 1. And then I can say 2k is greater than k plus 1. You see why that might be true? And now, we're going to use this part and this part. Do you see if any connection between them? 2k, so I can write down here, using the two things, that k plus 1 is less than 2k, which is less than 2 raised to k plus 1. Okay, so it's a k plus 1 is less than 2k, right?
Yes.
So we're right, that's why I wrote it right here. 2k, k plus 1 is less than 2k. Then I do the second part. That's 2k. 2k is less than 2 raised to k plus 1. 2k is less than 2 to the k plus 1. Yeah?
How do you come up with k is greater than 1?
Okay, from up here, it's saying it works for all positive and.
But why is it greater than 1?
Because, well, we have n equals 1 is we already did the first case, so we don't have to worry about the first case.
So it's what k is 2 and above.
Yeah. But because we already did the first case, we don't even have to worry about that. We know first case is true.
Yeah.
We said k equals 1, we tried it, it's true. Therefore, we want for all cases above that again.
What if you checked it and k is less than or greater than 0 and had it illustrated?
It would have been, you'd have to do a bit more magic. It would be much harder to do. You'd have to put a bit more descriptions in here. And like you'd have to describe why, and you might have to put a greater than or equal to, and then from a greater than equal to, transfer it into a greater than. But it's still doable. It just takes a lot more steps and a bit harder. Where? Right here? Here? Okay? No. If I did 2k minus k, what is 2k minus k? K. So 2k minus k is the same as just putting k. So basically I changed this k into this k, this 2k minus k. Now why did I choose 2k? Is probably the question you were going at. It's because we know in the problem, when we're trying to get to, we know we're trying to get to a 2k here. Because we need something that connects these two expressions. If we can't connect the two things, then this whole thing is meaningless.
How do you know your goal is to make yourself?
Okay? So the goal is always going to be if you plug in k plus 1 into both parts. So if you look back at this one, we stated our goal was, notice we stated by saying k plus 1 in place here, and k plus 1 on this side. So we put 2k and then plus the next step, which is k plus 1. In this case, we basically change this k into k plus 1, change this k into k plus 1. So now, do you see where this came from? Okay, now I'm going to simplify to say k plus 1 is less than 2 raised to the k plus 1. Because if a is less than b and b is less than c, then a is what compared to c? We use the transitive property, but yeah. You're familiar with the transitive property? Okay. Well, in general, we're just that if a is less than b and b is less than c, then a has to be less than c. I prefer to write it as triple, just so you can see that this thing right here applies to both parts here. And because this is true by mathematical induction, n is less than 2bn for positive n. Look at that. So notice we have ones like this. Yeah, 3 plus 5 plus 7 plus all the way up to 2n plus 1. Third, I'm adding up all the odd numbers. And I want to show that it's equal to n times n plus 2. How do we start? Case n equals 1. What do I write for this one? Okay, so you got 3 on one side, and what do we have on the other? Oh. you would want to write it out so that this is what you're doing. 1 plus 2 is 3, 1 times 3, 3 equals 3. Then, what do you do? Okay, well, you want to make a statement because this is true, something like that. So you need to make sure you're putting these words in. You can't just skip stuff. Because these are equal, case n equals 1 is true. Okay, what's the next thing? Okay, so after your words, I'm not going to write down. Assume. What do I assume? No. What do I assume? Okay. So remember, when you're doing your assumption, it is just your original statement without the k plus 1. Okay. Yes. And then you do k plus 1. So what am I trying to prove? So what is my goal? What's my goal? Yeah. We want to have the original case plus 2 times k plus 1 plus 1. Okay? Are these the same? Okay? If we just did this part, which case is just that part? Well, case k. Whereas, like, this part by itself is case k, which was in our assumption.
So that case k here plus 1.
Okay, no, it's up here. And if you look all the way to the top, there was a plus 1 already in it. If you look at just this part, this is case k. So we have to go to the step after case k, which is plugging in k plus 1.
Okay. Why there two?
What?
Why does it keep that?
Okay? Well, okay, we are this part right here is the same as this, right? Which is the case k. Yes, where we get if we plug in k. Well, we haven't got to the other side yet over here. So what would the other side be? K plus 1 times k plus 1 plus 2.
Why is that side not, if that added it on the side, why is it in this 1 plus 2?
Okay, so if you look at case k, that's what the statement right here is, right? Now, if we went to the case after k, we'd be plugging in the number after k, right? So if k was 5, we'd be plugging in 6. So if we look at this one right here, if k is 5, 2 times 5 plus 1, so this would be case 5. To get case 6, we're plugging in 5 plus 1, or 6. So we're changing it from the case and we're adding in the next step up, which is the k plus 1 case. Okay. What's the first step now once we have to get to this point? Or oftentimes, you're supposed to do using assumption, which is saying that all that pink part equals k times k plus 2. So that would be the next thing we're doing, is we want using assumption, this part equals that part. And then basically at that point it becomes just doing some algebra. Like algebra 1 type where we simplify one side, simplify the other, shows that they're the same. It might involve multiplying out, it might be factoring, all sorts of things that could be involved.